Let me say one more time. So it's the October 13th. It should with a camera on. All right. So those are the policies. And the first thing you have to remember, so is the Archimedean principle, the corollary, and the density theorem. Density theorem. Okay, so this problem is about statements, okay, precise statements. All right, this is similar to the problems in the first exam. Okay, so you have to memorize the exact statements. And the second problem is to use Archimedean principle for proofs. Okay, for this problem, sometimes you may need to combine with mathematical induction. So the second type of problem would be look like, for example, want you to prove a inequality involve natural numbers. So you probably want to apply Archimedean principle, but when you apply Archimedean principle, you may also want to use mathematical induction. Okay, it's a combined proof. Combined proof. All right, so the third one, okay, let me go to the next page. So the third one is definition of sets. Definition of sets and set operations. This includes, of course, union, intersection, and subtraction, symmetric difference, complements. And also the definition of a set, say A is a subset of B, or A is a proper subset of B, and A equal to B. Okay? So you have to know all those definitions. So how to define, for example, a set A is a subset of B. So the second one is A is a proper subset of B. Okay, a proper subset of B. So A is a subset of proper subset of B if A is a subset of B and A is not equal to B. All right. And of course, you still, when you want to define A is a subset of B, you have to say A is a subset of B if any X in A, X is in B. Okay, any X is in A, X is in B. And similarly, you can define A equals to B. So you have to know how to define it using mathematical language, okay? Mathematical language. And also there are some operations like union, intersection, subtraction, and symmetric difference. You also need to know how to write down the definition, how to define the union of two sets, the intersection of two sets, the subtraction of two sets, and the symmetric difference of two sets. Okay, so number 4 is the De Morgan's laws. Okay, so first you have to know the statements, And second is you know the proof. So the statements and the proof. Because this one, I've already stated in class, and the proofs are also given in class. So you should read your notes carefully, okay? The statements, both the statements and the proof. Okay. So let me go to the next page for problem number 5. So prove two sets are equal. Okay, so this is a problem ask you to prove two sets are equal. So you should remember the procedure, okay? The procedure is step 1. So say A equals to B. You want to prove A equals to B. You just, step 1 is to show A is a subset of B. So to show this, you get, you just let X be A and prove that X is an arbitrary element in A. You prove that X is in B. Okay, so step 2 is to show B is a subset of A. So to show B is a subset of A, you will let X be an arbitrary element in B and prove that X is in A. So after you prove that, After step 1 and 2, you can claim A is equal to B. So there are plenty of examples given in class. So to prepare for the last problem, problem number 5, you should look at the examples we gave in class. So understand the proofs of those examples, it will be enough, because the problems are going to be similar to one of those examples. So essentially, you should focus on the 5 things I just mentioned, and you read your notes carefully and you review your homework problems. Then that would be enough. That would be enough. Okay, so do you have any questions about the exam? Okay, so if you don't have any questions, let me go over one of the homework problems. Okay, let me look at the homework. Okay, let me go over homework problem 9.4. So first we want to, so problem 9.4 wants us to give a definition for interval. Okay, so using a different way, and so how to define this interval? Okay, so let me write down the statement of the problem. So maybe some of you. So A, we want to give a mathematical definition of an interval. Of course, interval. This means the interval in R. In R. So the definition should be the following. So let A be a subset of the real numbers. So A is an interval in R if for any two numbers, for any A and B in A with A less than B, and if X is between A and B, then X is in A. So So the definition, the mathematical definition of an interval in R is just a subset of the real numbers, so that if there are two numbers, two elements in A, okay, you pick any two different elements in A. Suppose A is less than B, and any other number between A and B, if you take any other number x between A and B, then x must be in A. In other words, any number between these two numbers have to be containing A. Then A must be an interval. Okay. All right. So this is the mathematical definition of an interval. And second is to use your definition, use the definition to prove that if A is a subset of R, is a non-empty interval with upper and lower bounds, then there exists A and B in R such that this open interval AB is contained in A, and A is contained in the closed interval AB. Okay, so B wants you to prove if you have a bounded interval in R, then this interval A must contain some open interval AB and contained in the closed interval AB. All right. So we have to use the definition in A. We have to use the definition in A. So let's look at the proof. So the key is because in here, we just want to prove there existing AB in R satisfies the condition. So the key is to find out A and B. So how to define A and B? I think this is already clear from the hypothesis. The interval is bounded with upper and lower bounds. So by the completeness of the real numbers, we know that there exists a least upper bound and greatest lower bound for A. So since A is not empty with upper and lower bounds, so by the completeness of the real numbers, A has a greatest lower bound. Say A, we use A as the greatest lower bound, and least upper bound. B. Okay, so A is actually the greatest lower bound, and B is the least upper bound for A. So next, we want to show the set capital A contains the open interval AB and contained in the closed interval AB. All right. So let me copy the condition. A is the greatest lower bound. And B is the least upper bound. All right. Okay, let's continue our proof. And we want to prove, this is we want to prove. So we want to prove, let me write it. A contains the open interval AB and containing the closed interval AB. Okay, so to prove the open interval AB is in A, it's enough to prove any number between A and B is contained in A. So, well, let say X be in the open interval AB, then we know that X is greater than A is less than B. Okay, this is a definition. All right, so you should we use the choice of A and B. Since A is the greatest lower bound, and X is greater than A. This tells you what? X is not a lower bound for A. Okay? Because X is a number greater than A. A is already the greatest lower bound. So X cannot be a lower bound for A. But what does it mean by X is not a lower bound for A? That means there exists a number in A which is smaller than X. Then there is a Y in A such that Y is less than X. So on the other hand, since B is the least upper bound, and X is less than B, so here X is less than B, X is not an upper bound for A. Because B is already the least upper bound, but X is smaller than B, so X cannot be an upper bound for A. X cannot be an upper bound for A implies there exists a number in A which is greater than X. So there exists a W in A such that x is less than w. Okay, now you look at these two conditions, y less than b, y less than x, and x is less than w. Then we have x is between y and w. But remember, this y and w are elements. Since y, w belongs to a, y less than w, and a is an interval. So remember, in the definition of a, we said that a is an interval if for any two numbers in a with one number less than the other, any real number between these two numbers must be containing a. So by the definition, in A, we know that x belongs to A. So this tells you what? This number x, we show that we take any number x in the open interval AB, we show that this number x is in A. Hence, we can claim AB is containing A. All right, so we proved one side, AB, the open interval AB is containing A. And then we want to show A is containing the closed interval AB. But this is the easier direction because since, so to show A is containing the closed interval AB, so we'll let, say, X be in A, an arbitrary element. We want to show X is between A and B. Now, since A is the greatest lower bound, so in particular, greatest lower bound is the lower bound. So we have X, A is less than X. And since B is the least upper bound, in particular, least upper bound is an upper bound, then we have X is less than or equal to, I would say less than, greater than or equal to B. So this tells you, hence, X belongs to AB because X is greater than or equal to A, less than or equal to B. Therefore, the set A is containing AB. So this is the easier direction. The harder direction is to show A contains the open interval AB using the definition of an interval. All right, so this proof is purely mathematical, and the problem C, D, and E are similar, but let me still prove at least C to let you look at more similar arguments. Okay, so the C wants you to prove, use the definition to prove that if A in R is a non-empty interval with an upper bound and no lower bound. Then there exists a B in R such that the open interval negative infinity to B is containing A, and A is containing the half open, half closed interval, negative infinity to B. So this is actually similar to B. The difference is in B, the set A has both upper bound and lower bound. But in C, the set A has only not, okay, this is empty. Not empty, okay. So in C, A has an upper bound, but no lower bound. In this situation, A is an infinite interval, so from negative infinity to B. All right, so let's look at the proof. So again, we want to define B. So in this situation, you know how to define B. So we just let B be the least upper bound. For the set A. Okay, because B has an upper bound by the completeness of the real numbers, you have a least upper bound. A has a least upper bound. All right, so let's first prove the open interval negative infinity to B is containing A. So we'll let X be in negative infinity to B. So this condition just tells you that X is less than B. All right, now since B is the least upper bound, so X is not an upper bound for A. So X is not an upper bound for A implies that there exists, hence there exists an element in A which is greater than X. There exists a in A such that X is less than A. Okay, so since the set A has no lower bound, since A has no lower bound, A has no lower bound. In particular, X is not a lower bound. X is not a lower bound. For A. So X is not a lower bound for A implies, so there exists, so there is a element Y in A such that Y is less than X. Hence, x is less than a and greater than y. Now, since both a and y are in a, by the definition of an interval, we know that x is in a. Since a is an interval, and ya belongs to a, by the definition of interval, we conclude that x is in a. So this shows that for any element x in negative infinity to b, x is in a. Hence, negative infinity to b is contained in a. So the other direction is always the easier direction because b is a least upper bound. Since b is the least upper bound for a, for any x in a, we know that x is less than or equal to b. So x belongs to negative infinity to b. Therefore, a is containing negative infinity to b, with b closed. So you can see this is very similar to b, except you just use the condition with a has an upper bound but no lower bound. Okay, do we have any questions? All right, so the proof of D, E, and F are just similar to the proofs of B and C. You can finish this after class. And remember, this Thursday, I'm going to have a Zoom session for questions. So if you have questions, you just come to the session. If you don't have questions, you don't have to come. Okay, so this is the same as last time. So you can ask any questions about exams or about homeworks, anything. Okay, do you have more questions today? All right, so if you don't have questions, so I'll stop here early, and I'll stay here for a few more minutes to see if anyone has questions. So if you don't have questions, you can quit the class now. Okay. Yeah. So do you want the second page? Mm-hmm. Okay, so it looks like you don't have questions right now, but you can think about it and prepare for the exam. And if you have more questions, you can ask me next time on Thursday. All right, see you on Thursday.